Update of this session, which is, by the way, urine collection. So we're going to go through the different stages of the nice circle: urine collection, session 1, urine processing, session 2, and then after lunch we will do fertilizer optimization, session 3, and fertilizer application, session 4. So the first update is by me on a project with Southeast Water, downstream effects of urine and its conversion to liquid fertilizers. So collecting urine is good, but the question that we had is, what does it do to the wastewater treatment infrastructure that was not designed for a situation with reduced urine? So this is what we are doing. It's one PhD project, so it's one of the small projects within NICE, but we are really generating some exciting data, as I hope to show you in the next few minutes. So project overview, I won't go through extensively because I already told you what this is about. We just want to assess not only the value of fertilizers that we produce from urine, but what are potentially the impacts of taking that urine out, because urine is only 1% of the volume in our sewage, but accounts for 80% of its nitrogen. It accounts for 50% of the phosphorus and a similar ratio for the potassium. So it's a big player when it comes to nutrients in sewage. Also, it is a big player in terms of the salinity of the sewage, so electrical conductivity, and also the alkalinity, so its ability to buffer against changes in pH. So things might not work in the way we know when we take some urine out of sewage. Sean and I published this paper based on modeling that was, I think, was it 2022 or even earlier? So we ran some models, BioWin for the wastewater treatment plant, and SUEX model together with my colleagues at UQ for the sewer network, and we found that everything looked mostly positive. So taking urine out of sewage would lead to a reduction in the energy consumption for wastewater treatment, reduced footprint of wastewater treatment plants, and potentially no impact on the sludge production rate, but we don't know about sludge characteristics. So this question triggered this project. Well, do we trust that model? That model is not built for situations without urine, so we need to kind of do something experimentally. But there's no place in the world where we can actually access sewage without urine, because, well, we do have some urine diversion here, but it goes straight into the sewer, and the sewer is not just generated by this building, so it's just merging with the sewage coming from upstream. So where can we go? Well, actually, that is the next step. We actually have not fully identified how to do a study on real sewage, but we're working with Southeast Water to try and potentially move into a next phase project where we are looking at the small catchment in a more regional area, and inspired by last year's talk by the guy from Vermont. What was his name? The American guy? Abram. Yeah. So over there, they actually had a system where they engaged people locally. They gave them jerry cans. People were returning the jerry cans and full, and they were getting empty ones. And there was, I think some token type of rewards. And I think that in an Australian context, we'll need to think about what a token would be. And in my opinion, it would be a cause of Woolies voucher, considering the cost of living crisis. And a lot of people would happily donate. But we'll need a small community, small catchment, so a small wastewater treatment plant. So if we can actually find one, and we're working on looking for one at the moment, then this would be quite an interesting project. But we couldn't wait for this. So with our PhD student, Chen, all we could think about is, let's just cook it up in the lab. And so we actually did this with synthetic wastewater. But we have a lot of recipes for synthetic wastewater that are working quite well. But in this case, we had to use 3 recipes. One for the fecal matter, one for the gray water, and one for the urine. And they needed to be tested and reliable. So there was a huge literature component here to actually find what a good recipe is. You stuff it up, you get the wrong recipe in, and all your data make no sense. So that is a little bit of the risk. But in the lab, we set up a few of these columns. They are bioreactors working in a sequencing batch mode. So in wastewater treatment, most full-scale systems are continuous, but a few sequencing batch systems exist. And we have some medium-scale ones in Melbourne as well. So this is, quite a valid way to test it with a sequencing batch reactor. Sequencing batch reactor, for those that are not wastewater experts, consists of filling the reactor with your wastewater and then doing several phases. So to simulate, so first we feed, and then we have an anoxic phase, no oxygen. That is what is done in a wastewater treatment plant. You have anoxic tank followed by aerobic tank. So here is anoxic stage followed by aerobic stage. So first no oxygen, then blow air through it to oxidize ammonium to nitrate and COD to carbon dioxide. That ammonium becomes nitrate. Then we need to reduce it to nitrogen gas. In a continuous system, this is done by recycling. In an SBR, is done by decanting only a small fraction of the wastewater so that the nitrate stays in, and then you can denitrify in the next loop. So I've got the recipes here, not that is very interesting, but you might wonder, how do we make feces at home? Like fake feces. And so this is actually a lot of people are quite curious about it. So I think it's a good engagement piece because everyone loves poo. And when you tell them you can actually make it in your kitchen, then it's even more exciting. So, but they're quite established, and it consists of mostly food ingredients, which is exactly what goes into poo in the first place. So yeast extract, cellulose. Right? Is that Vegemite? No, I mean, pretty much. But in the lab, we buy it as yeast extract, because you can't have food products in the lab. Cellulose, psyllium, miso paste, and then you add other elements. So it is not quite looking like poo, but it will have a similar organic content, similar nutrient content, a similar water content. So water in poo is typically, I think, 70%. So although they look solid, it's really still 70% water, and so we need to account for that. Interesting fact: we tried this, and it actually didn't work at all for quite some time, and then more literature research, and we came up with a few hypotheses that why. So the nitrification was not happening at all, and then after brainstorming session with the supervisors and the student, we added sodium molybdate. So it seems like those nitrifiers we're missing molybdenum, which is needed for some of their cofactors. Put that in, and it worked beautifully. So that shows you how difficult it is to work with synthetic wastewaters. Just how do you find that one missing ingredient? And so we actually got lucky. After that, it started working very well. But is this truly representative of real feces? Well, it's not going to be the same. So we really hope to be able to move into that next study, which probably will happen after the end of the nice hub, but it will be a nice follow-up. So, and the gray water is much easier because it's much better characterized. And urine, I don't even show it because we're now very, very good at making urine in the lab in a way that really mimics urine's composition, well, except for the 80,000 chemicals in it that are present in very small traces, but they're not going to affect what we're trying to do here, which is demonstrating how wastewater treatment works in the absence of urine. So quickly, a few graphs. So the one on the left here is base case, no urine diversion. So you can see the different phases here in different colors. So time is the x-axis, and then you can see the concentrations of the different nitrogen species versus time, as well as COD on the right axis. So in our case, about 45 minutes was the anoxic time that was needed to drop the nitrogen down to around 0.5 milligrams per liter, which was our criteria for end of anoxic. And then we start aerating. And when you aerate, you can see that the blue line takes off. That's nitrate production. The red line comes down. That's ammonia consumption, working quite well. Not much nitrite accumulation. And so we dropped to where we wanted to be, 0.5 milligrams per liter at about 140 minutes. So you can see the aerobic phase is going to be longer than the anoxic phase. But that kind of made us feel good about our recipe, because this is really as expected based on real sewage. So real sewage behaves like this. So we're happy with that. And then we started to take some urine out. So put less urine into the mix. So a 25% urine diversion on the right, you can see some changes. This confirmed the results of the modeling I did with Sean back then. The anoxic phase shrinks quite a bit already, almost irrelevant. 7 minutes and you're pretty much done. So that's very fast denitrification. And the aerobic phase, we are expected to remain the same. We're finding actually it takes a bit longer. And why? It's because while ammonia depletion is occurring as fast, you have nitrite accumulation. So the nitrite oxidation start to suffer somehow for some reason. But that is not a big deal here. But then when we go to 50 and 75%, this becomes a little bit worse. So again, those 7-5 minutes anoxic, we still have it simply because we need to feed, and it takes 5 minutes to actually put the wastewater in. So we still call it anoxic phase, but effectively, we don't need any anoxic phase. And that's what our modeling paper showed. So confirming that, because we have less and less nitrate in the system because we are taking the urine out. So we are working with reduced nitrogen loads. But the nitrite accumulation problem worsened with urine diversion. And at 75%, you can see that now you don't need any anoxic phase, but the aerobic phase has become much longer. And so that hits you back. Yeah. So this is our result. Are these applicable to real sewage and to a continuous system? We don't know. but at least we confirmed some of the modeling results. And but this is a warning. When we are removing all this urine from the mix, this potentially could be an issue. Like this is an issue for our synthetic mix. Potentially, likely will be an issue even with real sewage. So overall, though, there's been an improvement, confirming to some extent the modeling data from 2021. When you divert some urine, then you can feed more wastewater for a given period of time. And that's because when that nitrogen is not coming in, you don't need to spend time to oxidize it. And that's sort of the rate limiting step, oxidizing ammonia to nitrite, nitrite to nitrate. You drop those down, and so you can actually feed more wastewater. So therefore, for the same reactor volume, by diverting 25% of the urine, you can actually treat 30% more wastewater. So that's really the very promising result here, because a lot of our treatment plants are running at capacity, designed and built in the 1950s to 70s, with population growth and the additional challenges related to lifestyle and consumption. We're not able to treat more, but our catchments are growing. And so water utilities are looking at ways to avoid investing in large upgrade of infrastructure. And this could play a role. It is nice to see that you don't need to divert a lot. So that diversion, 0 to 25%, tells us that the moment you start diverting a small fraction, you already get pretty much the same percent benefit in terms of additional capacity. So you could accommodate 25, 30% more people in one catchment if you could take 25% of the urine out of the system. So, and if we're looking at 5%, it might be something that we can actually do in some of the catchments. Unfortunately, experimental data show there's no additional benefit. The modeling was saying that it was marginally getting better, but this data, because of the slow nitrite oxidation we did not predict with BioWin, tell us that we divert more urine and we don't get more capacity beyond that 25-30% mark. So that's quite an interesting result. That doesn't mean that it's not worth doing it. If we can, we really need that nitrogen and phosphorus to put back into our circular economy for food production at some point in the future, but we won't get benefits. At the same time, we're not killing it either. So that means, I mean, those bacteria are still working, the sludge is still working, and it's just not working better, but it's not dying either. So additional results that are being packaged at the moment by the students, so I don't have graphs. Sludge production per cubic meter of wastewater increases, but not dramatically. And that is expected. The modeling predicted that too. That's because we're transferring some of the anoxic growth to aerobic growth. And with oxygen, bacteria grow a little bit better. So we're making a little bit more sludge. And note that the COD, the organic matter, has not been diverted at all. We're only diverting nitrogen phosphorus. Good news, sludge volume index. So the settleability of the sludge has not been affected. So we ran these experiments over a period of 1 year. So there was plenty of opportunity for failure, but the sludge kept settling well. So that's good. That's really great news. And that's where we were concerned. We didn't know whether the sludge would start behaving strangely. Greenhouse gas emissions, the work is done. And overall, we're producing less, mostly looking at N2O. Because N2O is coming out of both nitrification and denitrification. And we're reducing it because we're not putting that nitrogen into the wastewater treatment. So, but unfortunately, per gram of nitrogen that goes into treatment, we're making more N2O. Just like the nitrite accumulation I showed you, we have more N2O production. More N2O production per gram of nitrogen coming in. Fortunately, because we are diverting some of the nitrogen, that nitrogen doesn't get a chance to form N2O. So overall, we are still doing better than base case. But the hope was we would kill it, but not really. But whether then this is applicable to continuous system and real sewage is yet to be determined. So one proposed collaborative project here is doing a life cycle assessment for greenhouse gas emissions for these fertilizers. Now we have shown that N2O production in the treatment has reduced, but how much N2O is going to come out when we use them as fertilizers? So, and how does that compare to conventional fertilizers? So this is for discussion later. And to conclude, this is future work for the next 12 months. Chen is going to look at the effects on sewer. So it's going to create, still in the lab, a rising main and the gravity sewer pipe. And there the idea is to work out with urine diversion what happens to the critical processes that occur in sewage, particularly formation of sulfide and formation of methane gas and potential release, and whether there's any effects on the microbial community that lives in biofilm on the sewer. So that's the update for this project. We leave questions for the end. So hold on, and just don't forget it. Don't forget your questions. But that's the way we're structuring it. That's because then those questions can become a little bit more interdisciplinary. So the next update is from Bezad, from UTS. Bezad project is a novel sustainable ground stabilization adopting calcium carbonate precipitation using urine.